Hi, I'm going to talk you through a very basic example on how to get the Kaplan Meier estimate of a survival curve. For this example, we're going to look at biostat data. It's an experiment or trial where we have patients placed on different drugs, and the effect is to see whether the drugs have different impact on the survival time. So our factor is drug, and we have the levels, drug A, B, C, and then there's a placebo. Okay, I have loaded the data. So let's see let's see what the structure of the data looks like. We'll just list the first three observations. What we have here is three variables. Death, which is the time to death. It's a very morbid kind of subject, but this is what it's about. And then treatment. Treatment is the factor, and that comes in four levels: drug A, B, C, and then the placebo. And then we need a variable status, and status is an indicator variable, otherwise known as a dummy variable. That is 1 if the person actually died, and it takes the value 0 if we have right censoring. So some individuals are still alive either at the end of the trial or that they've dropped out at some point, so we just know that they're still alive. So that's one of the good things about this procedure, because it can take account of right censored data. Okay, I want to get a feel for the data, so I'm going to just look at the table of the factors. So table of my data, and look at the treatment. We can see that there are 30 people on each of who experience each of these levels. So this is like if we think about an ANOVA analysis, this is like a one-way ANOVA, and it's a balanced design because we have equal number of patients or individuals experiencing each of these levels of drug, and they're not the same people, so this is a between subjects design. But we're doing survival analysis, and that's not about ANOVA. Still trying to get a feel of the data, we can look at the mean survival times across the treatments. So use the tapply command. Okay, if you do this, remember to either attach your data frame or do something like this with the data. This data frame, I apply this command, calculate the means of the survival time, mean survival time for people whose true survival time unknown, and we're plotting across the levels of treatment. So looking at this, if you just glance at it, it seems like the drugs, the survival times, the mean survival times, if you take any of the drugs A, B, C, is higher than the placebo, with the biggest difference between drug A, and the placebo group. So if we're doing a one-way analysis, our question would be, is the mean survival time the same or not across the levels of that drug? That was given an idea whether the drug has had an impact on the survival time. But as I said, that is not the aim of survival analysis. And since I just want to do the basic stuff, I'll come back to this again, ANOVA versus this survival curve at the end. Okay, to run this procedure we need the package survival, and then to get the curve it's very easy. The survival curve, it's using the command survfit. I'm going to plot it, and I can choose whether, let's see, I'm going to do this basic way first. I need an object first, so the object is the serve, and then the first thing is the time, and the second thing you need is data on whether it's been censored, so the indicator variable. And I can get this survival curve estimate of the survival curve, the KM estimate of the survival curve, over levels of a given factor, or here If I do tilde 1, that means I'm not doing it across any factor at all. So in this case, I should just get an estimate of the survival curve along with the confidence interval. Here you go. I've done a bog standard one, so I've not bothered to put labels. I just want to keep things as simple as possible, but adding labels is not going to be an issue, as we'll see later on. The x-axis here, this horizontal axis, denotes time, and the vertical axis here is the estimate of this survival function. You can see this estimate of survival function is a probability, so that's why it's between the values of 0 to 1. The dark line there, that's the actual estimate, as opposed to actually this true line, and the dotted lines are the confidence intervals, around 95% confidence intervals. We can see that the shape of the survival curve is going downwards, which makes sense because how you read this graph is that it tells you the probability that the person survives at least to a given point in time. So here the point estimate, probability that person survives to at least 20 periods, whatever that period is measured in, days or months, is that probability. So just under 0.1. So the beginning of time, probability obviously begins at 1 because everybody is alive, and by the end here it reaches 0 because everyone is in that trial is passed away. Now we can get the survival curve for different levels of the factor, because we want to see if the survival curves for the drugs, whether they're the same or not. So let's do that now. So as usual with this kind of thing, I've got all the code done first, and this code is available on the website. Alright, so I've run the same thing again, but instead of just on the 1, I've done now on the factor treatment. Okay, and then let's look at the plot. Here you go. So there should be 4 lines, one for each plot, but it looks a right mess and we can't actually work it out. In fact, it looks like a work of abstract art, doesn't it? So what we need is some colouring and some labels. Exactly, I'm going to redo it but add shadings and lines, and this part is not too interesting or important, but the code is there if you want to kind of work out how to do things. You can use the code and just edit it for your kind of case. So I'm going to plot this object, that thing that I've just fitted, and add labels. Okay, and colors 1 to 4 for each of these guys. Then I also want a legend. Now the legend I could have put in within this plot thing, but then the command just got way too long and not easily handleable, so I've just broken it down. So now I have legend that just adds the box. Okay, let's look at it there. Now this is a pretty nice picture, because if there is no difference on the impact of the drugs on our patients, then you'd imagine that all the survival curves would be very, very much similar. What we can see here is that drug A here is much different to the other ones, and if you look at it, it seems to be saying that it's prolonging people's lives. If you look at the placebo, the people that die off is slightly over 10, maybe 10, 11, 12, 13, something like that. For people on drug B and C, they're similarly like that. They've all died off by the time 19. We'll get those exact figures in a moment, so just wait. And the people on drug A, they're kind of like twice as long, isn't it, as people in drug B and C. They've lived over twice as long, because this is way over 40, maybe 50. So let's get those actual figures and pull out the confidence intervals as well, because that's something you'd like to know. So summary, and then just the thing that we fitted. Fantastic. So here you go. So we should have 4 blocks of tables, 1 for each level of the drug. Here you go. Drug A. So let's just look, each one will be the same. What they've plotted is time versus the survival probability that an individual survives to at least that time. We've got the standard errors for the estimates, because these are the estimate survivals, and then we've got the confidence intervals. So these would be the bands going around these survival estimate. I should mention that going back to this plot here, wherever we see a cross, that means that there's somebody that's been censored. So if we look at the drug A, the black line, there's nobody being censored. I can't see any crosses there, but in the blue line you can see some crosses. If we go to the placebo one now, along with the picture, because we could see that some people have been censored here, so let's see what happens. At time 1, number at risk, that's a full 30 people. Out of that full 30 people, number of 3 people that pass away are 3, that leaves 27. Okay, then we could do the same thing. Out of the 27, 2 people pass away, that leaves 25. And so you can kind of see the pattern, right? But there we go at time 3, out of 25 people, 1 person passed away, so we should have 24. However, look, it's only gone to 23, so we've lost 1. So around time 4, we've lost a person. So along around time 4, around here, there should be a cross somewhere for the blue line. And also around time 5 here, because out of the 17 people, 2 passed away, so we should have 15 left, but we've gotten suddenly 9. So we have 6 gone, so that's around time 5 that happens, 5 to 8, so there you got crosses. So that's the idea. At least that's the way I understand it, but then, you know, I am not a medic. Let's just make it clear that I'm not an experienced biostatistician. But I'm doing it because this is rather an interesting data set, interesting procedure. Okay, so the story so far is that we have got the estimates of the survival curves for different levels of a factor, and we've plotted them and we had a look at them. We looked at the confidence levels. So surely the next question is that once we've got the survival curve, are the differences in the survival curves across the levels of the factor? Because if there isn't, it means that the impact of those drugs, well, there isn't one. And if there is a difference, then that means some of those drugs must have some kind of effect. So how do we test that? Because we can't just look at it, you know, the plot's only suggestive. Now this is the next part of the procedure. You can do it or you might not need to do it. We can run a test. Okay, but before I do that, let me just say that I've got my story here, missed a bit out. So to finish off before I go to the test, you can, if you like, compare the median times of death across the levels. Okay, so what we got is that the median time of death for drug A 7, 10, C is 5, placebo is 8, and these are the lower level and upper level of the 95% confidence intervals. Now this, when I first looked at this, this kind of struck me because when we looked at the plot, do you remember that the for A it goes way out here, okay, than compared to the other ones. So why is the median it's like pretty much same in line with all the other ones? Well, if we trace back through the code there, look at the summary. Look, drug A, number of people surviving that long. Look, they're just 1, 1, 1, 1. Most of these events are occurring up here. Most of the deaths can see in bunches. In drug B, it's these events, quite a lot at the beginning, quite a lot at the end. The drug C, quite a lot beginning, quite a lot at the end. So, and likewise here. So in A, it's slightly different because you've got quite a lot of events happening at the start, and then it just kind of tails off. So these kinds of observations are more kind of isolated. Okay, so I don't want to hang myself by trying to say more than I have to. So if we want to go back to the test now, we're saying that we wanted to test the thing. Well, we have a choice of 3 tests, and in each case, the null hypothesis for this particular test is that there is no difference in the survival function across all 3 levels, across all the levels of our factor. In other words, survival curves are all the same. Versus the alternative that there's difference in at least 1 pair. Alright. So it's a bit like the ANOVA analysis. Remember, in the ANOVA analysis, the null is that there's no difference but across all groups, and versus the alternative difference at least 1 pair of groups. Here is we're not doing the testing of the means, we're comparing the survival functions. And there are 3 things we can do. We can run a log rank test, which is the most popular one. and we do that by setting row is equal to 0 in the command. We could run a generalized Wilcoxon test, and we can run the thing called the Tyrone-Ware test. As I said, the log rank test is the most popular. These tests operate, procedures work on a similar, as I understand it, work on a similar kind of, in a simpler way, except for how they differ is that the weights of the events, across time. So for the log rank test, they put more weight in the calculation of a test statistic on higher values of time. Generalized Wilcoxon, more weight on the lower values, and Tyrone-Ware test in between the log rank and Wilcoxon. Practically speaking, practitioners report that when it comes to the three tests, they give very similar results. So you'll see some people just run all three of them, and if they all kind of agree with each other, then poof, you don't have to kind of bother about which one you should choose from. Okay, and then there's some other notes that I've written down here, but anyway, we want to stick to the bog standard thing, so let's just run and interpret the results for all three of them. Let's start with the log rank, the most popular one. So recall that the null hypothesis, bear in mind that null hypothesis is that the survival functions for all of these levels in the treatment are the same. Okay, well, all we have to look at is this bottom line. This is how it's calculated. Null hypothesis, do we reject it? We look at the chi-square, it's 3.6. That's the test statistic. And then we'll go to the associated p-value, which is 0.312. The null hypothesis is that there is no difference in the survival groups. Survival functions are all the same across all levels. And since the p-value is big, remember the p-value stands for probability value, and the probability takes the value between 0 and 1. This p-value is big, it's bigger than 0.05, so we do not reject the null. Okay, if I compare it to the 0.05 figure, that's the same as conducting the test at the 5% significance level. And this chi-square is a one-tailed test. So just look at this figure, it's bigger than 0.05, so we do not reject the null. Conclude that we have evidence that there is no difference in the survival functions across those levels of the treatment. Since people find it hard to, or get confused about how to interpret the p-value, get it the wrong way around, when to reject, when not to reject, just remember this simple ditty. P is low, null must go. Alright, so P here is not low, it's bigger than a value, 0.05, so we do not reject the null. If I can say on the side here, it's actually better that we can state that we do not reject even at the 10% significance level, i.e. we do not even reject at its p-value is bigger than 0.1, so we do not reject even at the 10% significance level. So there's no evidence to reject the null. We kind of do the same thing now for the generalized Wilcoxon, so we change that row there to a, what was it, a 0.5. No, we change it to 1, right? So generalized Wilcoxon, just change it to 1. Here you go. And the p-value this is much higher, so again, we do not reject. Alright, and then 1.5, and I'm praying that they can give me the same kind of result. Yep, 0.69. So all three of them, we do not reject the null. Note that the p-value for the log rank test is lower than for the other two. Well, you can shut your ears if you don't want to hear this bit because it's not part of the basic stuff, but let's just have a look. Well, the log rank test places more weight on the higher values of time. We saw in the estimate of the survival function there was something way out towards 48, wasn't there? So the fact is that that's why the p-value is slightly lower, going towards evidence that there is a difference in the survival function because of that long right tail, right? And because it's placing more weight on that long right tail compared to these other two versions of the test, which places weight more towards the middle and towards the earlier observation time. Okay, so that's just about it. Let's bring this up again. So what have we done? We have estimated a survival function. We've kind of interpreted why, looked at an estimate of a survival function and talked about shape y, we'd expect it to be downward sloping over time. We've then compared survival functions across levels of a factor. Now I want to go back to the question of ANOVA. Survival analysis is different to ANOVA analysis. ANOVA analysis is just concerned merely with the whether there's a difference in the means across the groups. What we'd have found here is if we had run an ANOVA analysis instead, that there is no difference in means of survival time across the levels of the treatment. And I can tell you that because we found there is no difference in the survival function. Now, the survival function contains a lot more information than just merely looking at the means. So if the survival functions are the same, it must mean that all facets or aspects of this random variables across the levels must be the same. So if the survival functions for all the levels in the group are the same, it must mean that all kind of properties, features of those levels are the same. That includes the mean. So we can see that the survival functions are the same across the levels. It must mean that the means are the same. But if the means are the same, if we did an ANOVA analysis and found the mean is the same, does that mean that the survival functions are the same? You can kind of think that's a kind of a logical thing to say, put the statement the other way. The answer is no. You can have that the means across the levels are the same, but yet the survival functions across those levels could be different. Why? Because different survival shapes of the survival functions could give us the same mean. Alright, finally, what else can we note? Let's look at the pros and cons of this procedure, because it is one of the most, we'll see that it's most popular, one of the most popular methods used here for estimating survival curves. Pros, little assumption because it is a non-parametric method. Non-parametric meaning that we place no conditions, we do not assume anything about the distributions of the survival time. I.e., we don't make statements like, oh, we assume that the time is exponentially distributed or follows a Weibull distribution or some such thing. And also another pro is that it's okay for censored data. Con, it cannot include continuous covariates. Here we've looked at factors levels over the factor of treatment, which is categorical. Yeah, it's not continuous. If we want to do something that's continuous, we can't do that unless we change that continuous thing into categorical, which we can do by chopping it up. But then the results might be sensitive to how we chop up the covariate. For example, age is continuous. It could depend on how we chop that up. For example, we could turn it into categorical by saying less than 20, 21 to 30, over 30, or we could say let's create groups less than 15, 16 to 25, 26 to 40. Stuff like that. It could be sensitive to how we chop things up, so that's not great. It doesn't also quantify difference in the risk between the deaths of death between the levels of the treatment. We ran the test. All we could say is that there is a difference or there isn't a difference, and I was then searching around to see, well, with ANOVA, that if you find evidence of a difference across the levels, you then next go on to do tests to find out between what two pairs. But for this CARE procedure, once we do the test seems to just say that either there is no difference in the survival functions, or there is a difference in the survival functions in at least one between a pair, but it doesn't tell us like between which two pairs. Moreover, it doesn't tell us how much difference in the risk of death there is between like one level to the other level. To get these answers, we can kind of look at the next class of models, which are which place kind of more assumptions on the distribution of survival time, and these models are the semi-parametric models, being the Cox proportional hazards model, and fully parametric models, such as the proportional hazards model. But that's for another time. Okay, as I said, I'm not a biostatistician, so if there's anything I've made a mess of here, feel free to share. Okay.